Thank you very much for an introduction. Everyone hears me well? All right. So, good afternoon, everyone. It's a great pleasure to be here today with you and giving you a brief overview of what I have been busy doing in the past 10 years as a chemical engineering and material scientist, maybe five or five each year. So always when I start this talk, I start with the grand challenges. I would like to just take a moment and pay attention to what happens around us. So we do have a very complicated networks of the demand and supply, and we do not have a solution with the current rate that we are seeing in the population growth. These are highly relevant, they are highly interconnected to the extent that one factor here on this scenario can significantly influence the whole system. But talking about water energy nexus, and since we are in Nebraska, water energy and food nexus, which I explain in a second why that's even more important, we do have a demands of 100 quads or something around 15 terawatts energy by 2050. And do we have the solution for getting what we need? The answer is not necessarily known. So there's a complex correlation between water and energy supply. So we use water to create for providing energy, and we also use energy for providing clean water. On the other side of this triangle, you will see the groundwater resources influenced by the fertilizers and current practices in our farming. Here's a very, very brief overview of what's happening between water energy and food consumption. The real scenario is much more complex. I'm going to just take your attention for a moment and look at this chart. So here's the amount of the million gallon per day water being withdrawn from our resources, and here's West Coast. And you do have East Coast here on the other side. On the East Coast, we are mainly user, so we're basically using the water supply for providing energy. However, as we go beyond some lines, if you will, you start seeing the amount of the water used in irrigation is significantly high. And the public supply, the water that we use for our consumption, are not as nearly as significant compared to our water usage. But the question is that which one is more important? Do we have enough water that supply our own sustenance? And the answer is not, again, no. Here's the freshwater withdrawal and saline water withdrawals by the states, and the intensity shows how much we're using. As you see, as you go to the coast, the amount of the water withdrawals due to the access to the sea and ocean is significantly high. But in inland area, specifically in Nebraska, you can see that almost half and half. We do have surface water withdrawals and groundwater withdrawals almost equivalent. But what are the different technologies that we can use to desalinate water for potable water, for consumption, public supply consumptions? We can look at the traditional water technologies, or we can look at the new or emerging water technologies that we're using these days. The biggest argument when we look at these things are the energy arguments. Here's the typical numbers for the traditional methods, such as mechanical vapor compression, very popular when you are close to sea and have access to saline water. And here are the numbers for membrane-based technologies. So if you all agree, at least close to an order of magnitude, just from basic thermodynamic limit, membrane-based separation are winning this argument. So is that really showing us what's happening as deployment of this technology? And the answer is yes. Here are the number of these desalination plants we have in the United States that just work based on RO systems. Of course, when you look at the California, Florida, or even the areas up close to New York and Pennsylvania, you might see that more dot is appearing simply because you have access to the ocean. So here's the brief introduction to water desalination through RO process. I'm trying to open the system a little bit and show you what's happening inside the membrane module, and then tell you what exactly we do to design a membrane for the application or desired application we are pursuing. So basically the way reverse osmosis work, we are pushing water against the driving force. So here's the saline water or feed with the solute in it, and as a result of having solute in that water, you will have a osmotic pressure. In order to push the water out of the equilibrium, we need to provide energy. So we do pressurized water, and we use a semi-permeable barriers to let the water pass through and leave the salt behind. So here's a rough schematic. So you have a selective layer that allow water to go through and reject salt, and you have a support layer sitting under that, so it can allow you to physically support the membrane. When you are close to the ocean, you are lucky because you can just keep increasing recovery and dump the brine back into the sea. Basically, you're relying on the dilution by the ocean or by the sea. But as we go toward inland, this luxury is not available to us. So we need to think about solutions that are sustainable in the long term. So inside a water desalination plant, basically the water goes in. You have these membrane modules, which are pressure modules. And inside those modules, you're going to see membranes compacted or packaged inside the module. So here's the gold standard of the membrane that are being used in industry right now. So we do have a support barrier or support layer, often made of polysulfone, and we do have an active layer on the top of that. That active layer is almost 100 times bigger than the radius of a hydrogen atom. So it's a pretty tiny layer that provides that selectivity. Here's an image of that top layer. The green is the bottom section, which is the polysulfone, and the top layer is the active layer, which is polyamide. To just show you a little bit more how it's composed, basically it's formed through a roll-to-roll process. It's so easy to make it, so you can continuously make the support, and then it goes through a further processing for polymerization of that active layer on the top of this support. So here's the cross-section. In that cross-section, sometimes we have woven mesh to provide the additional mechanical support. We have that porous barrier that allows water to go through and support that active layer, which is pretty thin. Most of the research that has been done in the past 10 years on this subject are centered around working on that active layer. So there are challenges involved, as an example, permeability and selectivity trade-off, or having anti-biofouling membranes, because one of the most significant challenge in membrane-based process is how to avoid fouling of the membrane. So today I will mostly focus on the porous media because I'm going to introduce a new technology, which is not really new, but it's emerging for the past 20 years. So we should consider this technology as an important opportunity for allow us to use inland water desalination. So if you look at, again, water desalination, all these technologies, which are membrane-based, rely on a porous support that, based on size exclusion, allow for permeate to pass through and reject the solute. What do we know about the porous materials? So being a material scientist for almost 5 years, I learned that we can make any structure at any size from any materials we want. So if you're going to make a porous materials, you can make it from inorganic, or you can make it from organic materials. And it can be as small as a nanometers to as large as a couple of micron with precise geometry. So the challenge is not in making them. The challenge is that how to make them in a way that they are commercially viable. We can use them for the future deployment in larger scale. So in the beginning of this talk, I'm going to discuss porous matrices, how we make them, what is the processes that are involved to fabricate a porous matrix made of polymeric materials, which is basically used in any sort of membrane separation that relies on polymeric membranes. And then toward the end, I will discuss a new method that we have been developing for the past 10 years, relying on high precision coating of the materials on the top of any substrates. So when we talk about polymer, so basically having a molecule or that has multiple repeating units almost from the same unit, you can think about how to process that. The majority of the thing that has done in the polymer processing are through the either melting, extruding, or in some cases, we take polymers and dissolve them in a suitable solvents and then process them. If you're going to make a porous membrane made of a polymer, we need to process that in a way. Like any other solution, if you think about just the solution-based processes, and I will tell you why solution-based processes is more important, you can imagine that you are supposed to find a composition in which polymer in the solvent has the lowest possible Gibbs energy of mixing. That's a requirement for any process because we need to reach the equilibrium. Well, as I said, thermal processes are not really attractive because they're expensive. If you're going to find a solution that have possibility of the roll-to-roll processing, usually solvent-based processes are more attractive. So here's a ternary diagram. Here's a polymer. Basically, it's a composition diagram. Here's a polymer. Here's a solvent of the polymer. And here's a third component, which polymer is not really happy to be dissolved into. Basically, we call that non-solvent. So I don't like all these things on it, so let's take a look at the simple phase. So if you look at this diagram for any polymers, there are areas in which polymers are forming a homogeneous form. And there are areas that polymers become glassy, solid materials. There are areas that solvent and the other component, which we call non-solvent, do not possess the quality or sufficient energy to solvate the polymer molecule. As a result, we ended up with a swelling situation. So polymer swells because it's significantly a large molecule and it can intake solvent and non-solvent molecules in itself. And there are domains in which two-phase properties shows up. So we have a domain which are rich in polymers, and we have a domains which are poor or do not possess enough polymeric materials in there. When we talk about solution and polymeric materials, everything comes to the interaction at the molecular scale. We do have a long chain, and this long chain is interacting with the solvent. And everything can be simplified in terms of interaction energy between the solvent and the polymer. So luckily, 100 years ago, Gibbs gave us the required toolbox to be able to simulate this process. Here's an example. I have a polymer solution in that little dot. So basically, that's polysulfone. And now I'm going to add the third component into that, which in this case is water. Very similar to salt-out process, because polymer doesn't like water. When I adjusted the condition in this mixture, polymer prefer to precipitate. As a result, it come out from the solution as a solid. Basically, that's a principle that has been used for the past 30 years to make polymeric materials. And it's interesting and amazing. And we do not have any replacement for that yet. A little bit about the mathematics of this. So basically, the term here is a Gibbs energy of mixing. And here you have different components. And here you have that phase diagram. When we start from a homogeneous solution, we are here at the composition of a solvent and polymer. And that composition is the equilibrium and happy composition, if you will. If you force this solution out of equilibrium, what's going to happen is going to pass that boundary, and we ended up with a two-phase scenario. And that two-phase scenario is what we call membrane. Because soon after you extract the solvent, excess materials which left in the void, you will remain with a porous matrix. So we can simulate this. We can try to understand the effect of different parameters in the system, such as polymer materials itself, such as solvent and co-solvent, such as the molecular weight, thermodynamic, diffusion, and eventually design materials based on our needs. Here's an example. Here's a typical ultrafiltration membrane you're using, like polysulfone. Here we just change the solvent. We have NMP and we have dimethylformamide. So NMP is N-methylpyrrolidone, so two different solvents. Everything is the same, and you see the pore size and the structure is significantly changing. So we can tune this property by simply changing the bulk property of the solution. And here's the process simply in the industry too. They cast this polymer solution on a piece of substrate. It can be a polyester, it can be woven mesh, like a nylon mesh, and then they put this whole composite into a non-solvent bath, which they call it coagulation bath. As a result, solvent escape because the situation, the new Gibbs energy is not favorable, so solvent escape and the pore remains in the matrix. Here's another example from different materials. Here's a highly hydrophobic materials. And as you see, when we change the solvent from triethyl phosphate to dimethylacetamide, the pore structure and the structure of the material significantly changes. So how can we use this? That's an interesting property we can achieve for hydrophobic materials, because simply they do not like to interact with solvent. Majority of the hydrophobic material do not interact with solvent well, and we call them not easily processable. So there's a process called membrane distillation. As the name suggests, it's a distillation that has been assisted by a membrane or a porous barrier. The way it works is pretty simple. You have a hot water on one side, and you have a cold water on the other side. This barrier, or the membrane, does not interact with water well. So we call it hydrophobic. But it is porous. As a result, vapor or water vapor can pass through. So if you create a temperature gradient on the two sides of this barrier, that temperature gradient is translated to a pressure difference, and as a result, you can pass the solvent through this barrier. So let's say we have a brine here, or we have a salty water, and on the other side we have a distilled water. So we can keep increasing the flow of the water vapor from the salty sides to the clean water. As I mentioned, there are some criteria for this membrane, and the first one was non-wetting, because if the membrane wets, so water goes through and the whole process fails. Because if water goes through, salt goes through, so there is no separation. The second one and the third one are the structural parameters. You want to enhance the amount of the water passing through, because more water means more water per fixed amount of energy means more economic solution. So everything, the figure of merit in membrane distillation is kilowatt hour per meter cube of water. So if we can enhance the flux, basically we have a better solution compared to what is available outside. So it turns out from all the materials of interest, if you look at the properties that required for membrane distillation, polymeric materials are the choice. One of the reasons is simply because this process is thermally driven. So we do not like to lose the heat that is the driving force of the process. And one way to lose the heat is to conduct the heat through these materials or through that barrier. So if you have a material that has a very low heat conductance, you're going to have a best possible scenario in terms of choice of materials. So we started looking at different hydrophobic membrane or polymers to be able to make hydrophobic porous membrane for this process. Turns out that there are not too many hydrophobic materials that can be dissolved in the solvent and can go through a roll-to-roll process, because that's desirable. If you cannot have a roll-to-roll processing, the economy of the process is going to be under question. In membrane-based processes, one of the biggest costs is the cost of membrane itself. If you cannot make membrane at low cost, the process is not going to be successful and cannot be easily deployed. So we choose that PVDF or polyvinylidene fluoride, and we look at different solvents, and turns out that it can dissolve in many different solvents. And then we started navigating through the space of these parameters to see if we can find the proper configuration or proper operating condition for making a hydrophobic membrane suitable for MD process. Here's our first attempt. We look at molecular weight, and we look at concentration of that solution. And here, liquid interface, basically when we do that casting process, whatever is that interface of the liquid polymer is called liquid interface. And whatever is sitting on the substrate, we call that the substrate interface. You see, as we change the parameters of this process, such as molecular weight of the polymer or concentration, the structure significantly change. Most of these things are closed. Basically, there are no pores. So that was the first challenge we faced. So we made the materials. It was hydrophobic. It was porous, but the top surface was closed. So there's no way for vapor to go through. So the next was how to open this structure. So we again went after the processing condition. We start adding something to that third component, that non-solvent, which we call coagulation bath. In this case, we start adding a little bit of a 2-propanol, less than 10% volume. And we start seeing that as we increase the amount of the propanol in that coagulation bath, the structure of the top surface is opening up. So we can create membranes with the desired surface porosity. It turns out that the same property or same action result in changing up the surface topography. Basically, the height of the surface is changing. And that has an effect on how the water interacts with the surface. So if you have a surface which is it has significant heterogeneity, you have air and you have surface on it, air can sit behind or occupy the place where the water can sit. As a result, it's going to repel water. So we started looking at the different properties of this membrane, and we look at the flux. What we learned was that the higher the 2-propanol in our coagulation bath, meaning the higher the surface area, open surface area, we could get higher flux. And we could achieve about 30 LMH of flux for this membrane. So if that's true, so the highest possible opening means the best membrane possible. So can we do that? Do we have the required toolbox to create a highly open surface and adjust the surface property so we can repel water, let the vapor go through, and enhance the flux by adjusting the structural parameters of this design? Well, we tried to give it a first shot. We know that there is a gap in material processing technology. We knew that. So our first try was to make an absolutely open structure. Look at the flux value. It went up to 80 LMH. But we pay something for that. After 20 minutes or 25 minutes, the salt starts diffusing through this membrane. That means it's a failure. So we need to adjust the pore. We need to make it open enough, but we need to adjust the pore in the meanwhile. Otherwise, the water will break the meniscus at the entrance of the pore, and as a result, the process fails. We try to come up with the best possible solution-based process that we could apply to the top of this membrane to adjust the pore size. Here's what you see. We basically have something very similar to a painting brush. We wet that painting brush with a new polymeric solution, and we paint the top surface of that mat. What happens is that when you do the coagulation, you start getting much denser structure. So you address the problem associated with meniscus breaking and water goes through, but as a result, you're losing the flux again. So we do know there's a technology, we do realize there's a technology gap in material processing. Here's the coating quality. So here's the individual fiber. We cut them. And you look at the coating quality, you don't see that much around it. And here's also the top image of those fibers. As you see, there's not that much of a control over this structure. So let's think about how we can make this membrane more productive. If you think about a flat sheet of membrane, and you're going to use it for high volume water production in any membrane-based separation, you need to package it. The way it's done in RO, basically a membrane is folded on itself, then it's rotated around the collector. And because you have pressure in the system, the membrane can be inside a pressure vessel. In membrane distillation, the driving force is heat. We do not have pressure. And if you go with the flat sheet geometry, basically if you put any excess pressure, water wet the membranes, and the process fails. And if you're going to design any module, like a plate and frame module, you are going to spend a lot of volume just creating a module and getting a little water. So the best approach is to turn the membrane around itself, create a hollow fiber membrane, and package that hollow fiber membrane in itself. Basically, that's the same membrane we're using in ultrafiltration. So here's the general schematic we had. Let's say we have a membrane inside a packing module, and we ask ourselves, can we first understand or simulate this process to see how much water we can take out from this module? Let me tell you about maybe my overlook, what I see in the future with this thing. I like to see a farm, or I like to see a place in which sun hits a solar, with a solar collector, we get the sun energy, heat up the water, and we have a small module somewhere in that house, and we get the water we need. So we don't need to pipe water. We don't need any pressure. We don't need to spend so much money to collect basically to deliver the required water to the household. So this can be one integration that, just like a solar cell integration with many different technologies, can be very useful for water filtration. So here's the initial result we had. I'm going to tell you exactly what they are in a second. But what I want you to pay attention is just we look at the permeation flux as a function of different properties of the module that we designed. Here's the first one, effect of packing. So as you know, if we pack more membrane in less volume, we should get more flux. This is expected, and we do see that. There's an additional effect in here that is hidden, and that's the thermal efficiency of the process. Here you see the radius of this fiber, and here you see some sort of indicator of flux. These are the length of the fibers, how long they need to be. And again, as you see, we can achieve significantly high flux for membrane beyond certain range in diameters. Basically, what we're trying to do, we're trying to identify the parameters of the membrane we need to make in order to produce water at lower cost. And here's the thickness of the membrane. The smaller the thickness, the less pathway for water to transfer. So if the water transfer faster, you get higher flux. And it turns out the most interesting one is the spacing of these fibers, because we do see some sort of initial raise as the flux, as these fibers are getting closer to each other, and then a sudden drop. Here's the R over A ratio that is on the axis, and here's the permeate flux. So in that case, basically when they're coming very close to each other, we're losing significant amount of flux. So we need to have a thin membranes, right length, exactly well separated in a right configuration. So here's our attempt. So we start making a membrane, basically a hollow fiber membrane. The thickness of this membrane is right on the range, 60 microns. The diameter is sized, so we know exactly how much it should be because we simulate the process. And then we can mass produce that if we want. And this has been done not for this specific material, which are hydrophobic, but for ultrafiltration membrane. And then it's come about the packaging. This is where we use additive manufacturing. Basically, we can make any packaging with any geometry down to 10 micron or 20 micron using current 3D printers. So we are at this stage to test this and test our hypothesis. We are excited to see what happens, and we are getting a lot of commercial requests for partnership these days. So that's why I usually don't show all the things beyond this point. But here we set up the cells. We are in the process of putting that together, and we will show more results soon. But what about the gap in the material processing technology? That's the second part, which I'm very passionate and excited about. I've been working on this for almost 5 or 6 years, and we come up with a solution, a scalable solution, to adjust the surface property at nanoscales. We can apply any coating of any polymeric materials at any scale you will. So the second part of my talk is going to be high precision coating. So if you think about polymer processing because polymer is the biggest word in the news these days, according to what I searched last time. If you search polymer in Google, the number of the hit you get on Google is way more than carbon. So polymer is getting significantly more attention compared to what it has in the last 10 years or so, I would say. But in terms of polymer processing, we are still lagging behind. So you can think about solution processes, which I talk about briefly in the beginning of my talk. So there are a variety of that you use for everything around you, coating, brushing something, coating a car, everything that you can imagine around you made of polymer and plastic has been through a solution processing. We can think about in situ polymerization, very familiar things when you go to a dentist. And there are pretty precise methods to make materials. And we do have a thin film deposition methods, which are more advanced but costly because they are typically go under vacuum. So each of these processing conditions give you a capability to do something at a different length scale, for different purpose. What if we can have a solution for all this to combine all these three together? So we came up with the idea of this initiated chemical vapor deposition, and I've been working on the development of this process. This came from my advisor lab like 10 years ago, and I have been working on that continuously to see what other possibility we can have from this method. So it's a liquid-free process. There's no liquid involved. And the way it works, we synthesize the polymer at the place we need it. If you want to apply a coating to something, you just coat the polymer where you need it. And we can control the properties of the polymer. That's the most interesting part about it. The way it works, we bring a gaseous mixture of chemical to a chamber and then initiate the polymerization at the surface. So basically, if you're going to coat a surface with different materials made of polymeric materials, you can just imagine putting that in the coating chamber, close the door, and open the lines so the monomers, the molecules that react, come absorb on the surface and then react on the surface. So the way it works, initially we break the monomers, we initiate it to a radical. The radical absorb on the surface of the materials that you wish to coat, and then that radical attacks a monomer, which is the single units for a polymer, and form a monomer radical. That monomer radical go through a propagation reaction. Basically, it finds another monomer on the surface, it reacts. Then another monomer on the reactor attached to it, and continue this process till the radical terminates. So this is the schematic of the filaments located inside this chamber. The gas molecule comes in here, initiator breaks on the filament, attached to the surface, along with monomer, polymerized on the surface. And there are a bunch of different chemistry that has been, in the past 10 years, has been explored. They are pretty interesting in terms of free radical polymerization, ring opening polymerization, and I have contributed to oxidative polymerization, which is also very interesting family of these polymers, these polymerization techniques. So you can think about R residue or R, the side chain of this monomer, which is a vanillin monomer, to be anything. So we can adjust the surface any way you want because we can bring functionality to a surface which is robust because it's a polymer. Here's an example. Cellulose acetate was a choice of materials for RO membrane back in '80, before thin film composite membrane came to market. These are extremely hydrophilic, meaning that water basically seep through. That's why they like the idea of using cellulose acetate in RO membranes. Here's I have a less than 8 nanometer coating that I added through this chemistry to the top surface of the cellulose acetate membrane. Here's a spectroscopic electron spectroscopy signal. Here's the cellulose acetate, and you see that the signature of cellulose acetate still is in the signal. And here's the CF2 band, which is a result of adding that CF2 on the top of that layer. As you see, the water doesn't even wet the surface. So we can adjust the surface property easily. So I hope I can show you this. So two materials are coated with the same topography. Everything is the same. We just slightly put coating on this materials, and this materials is the same. It's basically initial materials. See, the water even doesn't like to stay on these materials. It bounces off and goes. However, here you see the surface is being wet. What that takes me is going to be the next situation or next issue I initially mentioned. We do have a gap in the technology of coating technology. So, but that gap can be completely closed if we apply such coatings to the top of the highly open structure and create ultra high or a strongly non-wetting membrane for membrane distillation. So in conclusion, I would like to again point out to the DIPS, which is a diffusion-induced phase separation method, as a very, very strong or very robust method to make polymeric structure. I also showed you that how easily we can close the technology gap in the MD and make much stronger, much attractive membranes and address the challenges in the MD world. And lastly, I show you the CVD polymerization, which is a new technique for adjusting the surface wettability and chemical entity of materials at the surface. It's getting to the time that I am losing the control of my voice. So with that, I would like to just tell you that where I'm going with this. So if you put these two together, you should be able to cover the whole range. Instead of 50 micrometers or less than 10 nanometers that we can achieve, we can create any structure and basically coat that with a high precision. So we can have any surface we want with any property we want. Not only we can close the technology gap, we can also create new things, new materials, and metamaterials that can bring us new properties. What I'm targeting in the future is transport processes from three different perspectives. I'm interested in mechanical stability of materials. I'm interested in tuning chemical properties of materials. And I'm also looking at transport property of the materials at the molecular scale. I think with that, I'm going to thank the people who helped me get myself here today, my student mostly, and I would say my undergraduate students who have been working very hard in the lab as well. And thank you very much for your attention. I would be glad to take your question.
So your work certainly at this point is clearly emphasizing the development of effective materials. Many of us here work in the area of or are particularly interested in applications. And so I'd maybe appreciate a little bit more of your thoughts on potential applications, specific applications, and certainly what do you imagine the practical cost of, use of these materials would be? And then finally, is there the potential for reuse or the singular use materials?
Thank you for the question. Well, I start with the last one. Can we reuse them? Well, as I mentioned, the biggest problem in membrane is fouling. We know that. So it's usually a irreversible process because after bacteria start colonizing on the surface, it's really hard to remove that EPS residue on the surface. But if you imagine a surface which is non-wetting, or even we can impart further oleophobicity to that surface, not only repelling water, it also repelling organic materials with lower surface energy. Basically, that surface is self-cleaning. As a result, we would be able to imagine a situation that we have a membrane there. It's going to fail unless it's mechanically being damaged. So if we can adjust the property in a way that that module that we fabricate is not basically exposed to any physical damage, I would assume they can be sustained for a long time. In terms of cost, I think PVDF is pretty standard polymeric materials right now. It's being used on a daily basis everywhere. The cost of fabricating PVDF is almost on par with the polysulfone or even other polymeric materials. I would say polysulfone is even more expensive. And I think I missed the third question.
Applications?
Oh, this is. At this point, I'm just thinking about one household have enough supply for getting the water from the well and just put it into a membrane distillation. And why I'm so interested in that is basically here we are dealing with a 100% rejection for a membrane. That means it just doesn't give us the water we need. It just removes all the unwanted chemicals, such as those that we see often in eastern Nebraska are more of a challenge, like nitrate, I guess, everywhere, but we can also think about uranium, strontium. Because it's 100% rejection, we can avoid entering those chemicals to our water supply.
I had a question. Has anyone come up with an estimate on the difference in energy cost between membrane distillation and traditional distillation?
So the cost, yes, the cost is the biggest issue always. But here the cost can be minimized. And why I'm saying that, so we're not heating up the water to 100 degrees C. So we're heating up water at maximum to 60 degrees C. And that energy is, if you just use a regular solar collectors, that energy is sufficiently there for us. The idea of integrating this technology with heat waste has been out there for a long time. Turns out there are not that much of a heat waste. But solar energy is out there, and solar collectors. We have done the initial calculations. We know that if we integrate a solar collector to a module with the size that I just discussed in our simulation, we can be well beyond what is done with the typical FO, or close, getting close. We can get close to RO process easily.
What about the cleaning? Does it require intensive cleaning as the normal membranes that are out there in the industry, like ultrafiltration and reverse osmosis?
Let's see if I understand that question. You're asking what are the cleaning methods that are being done?
The cleaning of the membrane after several runs, does it require some cleaning? Is it something that you have evaluated already?
Sure. We're thinking about a hollow fiber module. And the beauty of hollow fiber module is that the feed is always on the external and in the shell. The cross-flow velocity is enough. If we get contamination or fouling on the surface, would be sufficient for cleaning those hollow fiber modules. I think in general, in membrane-based separation, when we have a dense layer, such as what we have in RO, we do have to go through osmotic backwash or continuous cleaning with chemicals. But here, we deal with the self-cleaning surface, and the chance that this surface gets contaminated with oil is less, and as a result, bacterial growth is going to be delayed. But if that happens, I would assume that cross-flow would be sufficient to clean the surface.
The other question that I have is in terms of the applications. Do you think that it is a technology suitable for reuse of wastewater? Like talking specifically about food industry wastewater.
It's a very interesting question. We have tried this with the flat sheet before. There's a fouling when we do flat sheet membrane, and that's all matter of if we can create even more surface cleaning. It's just a matter of adjusting the surface property of the materials. But right now, even in oil industry, they're after this technology because they know that if they can separate oil from water using MD, they can deal with that produced water. And I hear that this is being implemented, and there are companies working on it.
Anybody else? I have one last question. Is there an upper limit in terms of dissolved solids for purification of water using a membrane distillation method?
Sure. Well, that's an absolutely valid question to any membrane-based processes. In RO, we do have the problem, or in FO, we do have the problem dealing with the correlation, nonlinear correlation between salt concentration and osmotic pressure. So beyond some limit, the pressure requirement is significantly go high, and as a result, highly saline or hypersaline water are difficult to treat with water. In MD, the challenge might come when we have a highly concentrated solution in contact with the solid boundary and crystallization take place. So we are thinking about understanding crystallization at the interface of hydrophobic materials and water. We think it's more of a challenge in RO or in materials that water wet the surface. And in non-wetting surface, we expect that the crystallization occur, but it's not going to be as significantly common to what we see in other materials.
All right. Well, thank you very much.
Thank you.